Welcome to this presentation on causal inference for anomaly detection in cloud-native systems, methods and applications. We'll explore topics such as importance of causality, 3 pillars of causal anomaly detection, building an observability pipeline, hybrid SCMs for enhanced accuracy, tooling for causal inference, real-world application, query service example, need for benchmarks and case studies, roadmap for future practices, and closing thoughts and next steps. Understanding correlation versus causation is crucial. While correlation indicates a relationship, causation reveals the underlying why behind an anomaly. By identifying root causes, we achieve faster and more effective remediation, ultimately reducing false positives in our detection systems. This clarity empowers cloud-native systems to respond intelligently to anomalies. Structural causal models provide a framework to understand relationships in our systems. The potential outcomes framework allows us to reason about what could happen under different scenarios. Invariance-based approaches help us adapt to changes in the environment. When combined, these pillars create a robust foundation for enhancing anomaly detection capabilities in cloud-native systems. Start by collecting raw data directly from Kubernetes, capturing essential metrics. Transform this data into service dependency graphs that visualize interactions. Next, utilize structure learning algorithms to discover the underlying causal structures within your data. Finally, feed these insights into causal models that enhance anomaly detection, allowing for proactive monitoring and response. Combining domain knowledge with data-driven structure learning enhances accuracy in anomaly detection. We begin with an expert graph that steers causal discovery. By validating causal links through in-platform experiments, we ensure reliability. Finally, documenting interventions fosters reproducibility in CI/CD processes, paving the way for robust cloud-native systems. Open-source frameworks like DoY and EconML are pivotal for simplifying causal effect estimation. They provide powerful libraries that enable advanced analysis and insights. Furthermore, quick implementation examples allow for a practical understanding of these concepts, making it easier to apply them in real-world scenarios. Metrics and logs are essential for analyzing service performance. By creating causal graphs, we can visualize interactions between services. Implementing targeted interventions allows us to observe the effects directly. Finally, comparing results helps validate the causal relationships we've established, ensuring our analysis is robust and actionable. The field of causal inference for anomaly detection is hindered by a lack of documented production-scale examples. We must foster collaboration between vendors and academia to bridge this gap. Establishing standard benchmarks will drive consistency and reliability in methods. Moreover, open datasets are critical for supporting ongoing research and development, enabling real-world applications to flourish. Integrating domain knowledge with structure learning can elevate our anomaly detection efforts. By leveraging tools like DoY and EconML, we can streamline our processes. Automating causal inference within CI/CD pipelines enhances efficiency. Finally, establishing robust observability frameworks will provide deeper insights into our cloud-native systems. Causal inference is quickly becoming an essential best practice for anomaly detection, transforming incident responses from reactive to proactive approaches. I encourage you to dive into additional resources and tools that can help you innovate in this area. Thank you all for your engagement. Together, we can revolutionize back-end systems.